Before the turbines arrived, the river moved like a continent breathing. Season after season, it flooded valleys, buried farmland beneath black water, and carried entire forests downstream with a force no government could control. Villages adapted to it. Engineers feared it. Empires tried to map it and failed. The river existed on its own terms. Then came the promise. A machine so efficient it could turn falling water into industrial power with almost no wasted motion. A rotating system of steel blades and pressure chambers designed to capture the energy of gravity itself. No smoke, no coal ash, no locomotive convoys feeding furnaces day and night. Just water entering a turbine and electricity emerging from the other side. It sounded almost clean. By the middle of the 20th century, governments were racing to dam entire river systems around the world. They called it modernization. Factories would multiply, cities would illuminate. Nations would industrialize faster than ever before. The turbine became more than a machine. It became a symbol of national destiny. But rivers are not pipes. The more efficient the turbines became, the more water engineers demanded. Tributaries were redirected. Valleys disappeared beneath reservoirs. Fish migrations collapsed. Entire communities were relocated to feed rotating steel hidden inside concrete caverns larger than cathedrals. And in some places, the machines became so effective at extracting energy from water that the rivers themselves began to die. Not through explosion, not through accident, but through efficiency. Because the most dangerous industrial systems in history are often the ones that appear almost invisible. Long before hydroelectric turbines transformed rivers into industrial engines, civilization depended on energy systems that were slow, filthy, unstable, and brutally inefficient. Coal powered the 19th century because almost nothing else could. Factories consumed it by the ton. Railroads burned through entire mountains of it every year. Steel mills inhaled it without pause. Cities darkened under soot because industrial growth demanded combustion at a scale human beings had never witnessed before. Every new machine required heat. Every new railway required fuel. Every expanding city needed power plants that could operate day and night without interruption. And the deeper industrial civilization pushed into the 20th century, the more impossible the old system became. Coal extraction was already destroying workers by the hundreds of thousands. Entire mining towns existed under permanent black dust. Men descended underground before sunrise and emerged hours later coughing blood into cloth rags darkened with carbon. Tunnel collapses buried crews alive. Methane explosions ignited shafts with enough force to erase entire mining operations in seconds. In some regions, miners died so frequently that replacement labor became part of the economic calculation. But even this violence could not satisfy demand. Industrial nations needed more electricity than coal alone could realistically provide. Urban populations exploded. Manufacturing expanded into chemical production, electrified transit, aluminum refining, and military industry. Every new electrical system multiplied consumption. By the early 20th century, governments began to understand a terrifying reality. Modern civilization was becoming electrically hungry faster than existing fuel systems could sustain it. The problem was not simply production, it was efficiency. Early steam power wasted enormous amounts of energy. Coal had to be mined, transported, burned, and converted through multiple mechanical stages before electricity finally emerged from a generator. Heat escaped continuously during the process. Boilers ruptured. Turbines overheated. Entire rail systems existed primarily to feed fuel into industrial centers already struggling beneath pollution thick enough to blot out sunlight. Some cities became mechanical lungs, choking on their own growth. London, Pittsburgh, Essen, Manchester. Industrial smoke settled into streets so densely that midday resembled dusk. Buildings blackened beneath sulfur residue. Rivers near manufacturing centers turned chemically dead. In winter, coal smoke mixed with fog to create poisonous air that suffocated thousands. Children developed chronic respiratory disease before adolescence. Factory workers inhaled metallic dust beside furnace heat, strong enough to blister skin from several feet away. Industrial civilization needed power, but the existing method was poisoning the civilization producing it. At the same time, another problem was emerging far from the factories themselves. Rivers were becoming obstacles to modern expansion. Before large-scale hydraulic engineering, major rivers behaved unpredictably. Seasonal floods destroyed harvests and isolated towns. Drought periods crippled agriculture. In mountainous regions, water flow fluctuated violently throughout the year, creating cycles of destruction that governments could barely manage. Entire economies remained vulnerable to seasonal hydrology. Engineers saw wasted energy everywhere. Every waterfall represented untapped force. Every canyon represented pressure potential. Every descending river carried kinetic energy large enough to move steel, drive pumps, power mills, or generate electricity if someone could control it efficiently enough. Humans had already used water for centuries, but old water wheel systems were primitive compared to industrial needs. Traditional water wheels suffered from severe limitations. They depended heavily on local river conditions. Many operated inefficiently during seasonal flow changes. Rotational speed remained inconsistent. Mechanical output fluctuated constantly. Most importantly, water wheels could not scale to meet modern electrical demand. Factories required stable rotational energy. Electrical grids required consistency. Heavy industry required massive uninterrupted power generation. Old hydraulic systems could not provide it, and yet rivers continued moving day and night with enormous unused force. The challenge became an obsession among engineers throughout the 19th century. If water could be controlled with enough precision, entire industrial systems might operate without relying exclusively on combustion. The dream was seductive because it promised something almost impossible for the industrial world at the time. Continuous energy without continuous fuel transport. No endless coal trains. No furnace ash. No smoke-filled industrial skies. Just gravity, water pressure, and rotational motion. But controlling rivers meant confronting a scale of engineering unlike anything humanity had attempted before. A river is not a machine component. It shifts sediment. It changes course. It floods unpredictably. It destroys structures through erosion measured not in years, but in generations. Early dams frequently failed because engineers underestimated hydraulic force. Masonry cracked beneath pressure loads they barely understood mathematically. Spillways collapsed during flood seasons. Entire construction projects vanished beneath moving water. And behind every failed attempt stood another reality: labor. Building hydraulic infrastructure before modern machinery required armies of workers. Thousands of men excavated foundations with hand tools, dynamite, and primitive drilling systems. Tunnel crews blasted through granite beneath mountains under conditions resembling underground warfare. Concrete workers operated beside unstable forms, capable of crushing bodies instantly if structural pressure shifted unexpectedly. Death became routine around major water engineering projects long before the turbines themselves were perfected. But governments continued funding them because the industrial pressure kept growing. Electricity changed everything. Once cities became electrified, there was no return to older systems. Electric lighting extended industrial productivity into the night. Electrified rail systems accelerated urban growth. Aluminum refining, chemical processing, and communications infrastructure all depended on expanding power generation. Demand no longer rose gradually. It exploded. By the early 20th century, entire nations began reorganizing themselves around electrical infrastructure. The problem was no longer simply producing power. The problem was producing unimaginable quantities of it continuously, and coal alone could not safely carry the future industrial world being constructed. Oil helped, but oil introduced geopolitical dependency and enormous transportation networks vulnerable to war and instability. Steam systems remained mechanically wasteful. Wind and solar technologies were still primitive and incapable of supporting heavy industry. But rivers already possessed the energy nations needed. The question became whether humans could extract it efficiently enough to transform civilization itself. This is where hydraulic turbines emerged not merely as machines, but as solutions to a civilizational bottleneck. Engineers realized that efficiency was the key to everything. A slightly more efficient turbine could generate vastly more electricity from the same water flow. Increased efficiency meant smaller losses during energy conversion. Smaller losses meant lower operational costs. Lower costs meant larger electrical networks. Larger networks meant industrial expansion on a national scale. Hydraulic efficiency became an industrial obsession because rivers were finite systems. There was only so much water. If a turbine wasted too much energy through turbulence, friction, or poor blade geometry, entire generating stations lost enormous productive capacity. Governments and industrial companies began treating turbine design like military technology. Blade angles, pressure recovery systems, rotational speeds, and fluid dynamics became matters of national importance. The machine was no longer simply generating power. It was determining how aggressively civilization could expand. And as turbine efficiency improved, something dangerous happened. Industrial planners stopped adapting to rivers. Instead, rivers were forced to adapt to industry. Entire landscapes began changing around the logic of power generation. Valleys became future reservoirs on engineering maps long before communities living there understood what was coming. Water flow calculations started determining agricultural policy, regional development, and infrastructure placement. The river ceased being part of nature. It became raw industrial input, and the more efficient the turbines became, the more aggressively engineers pursued complete hydraulic control. Because efficiency creates appetite, and industrial civilization is rarely satisfied once it discovers a system capable of feeding its growth. The modern hydraulic turbine did not emerge from a single invention. It evolved through desperation. By the early 19th century, industrial nations were already exhausting the limits of older mechanical systems. Textile mills expanded faster than riverside infrastructure could support them. Mining operations demanded stronger pumps to remove groundwater from deep shafts. Ironworks needed reliable rotational force, capable of operating continuously under increasing industrial pressure. Water had powered machinery for centuries, but traditional systems belonged to a smaller world. The industrial age required something else entirely. The breakthrough began in France during the 1820s, when engineer Benoît Fourneyron developed one of the first practical water turbines, capable of operating at rotational speeds previously considered impossible. Unlike traditional water wheels, which relied heavily on the weight of moving water, Fourneyron's design exploited pressure and velocity with far greater efficiency. Water entered curved channels and struck rotating blades in controlled sequences that minimized wasted motion. The results stunned engineers. His turbines achieved efficiencies approaching 80% under ideal conditions, a figure almost unimaginable for the period. Factories that adopted the new systems suddenly possessed dramatically more usable power from the same water source. For industrial Europe, this was not a curiosity. It was a warning. Whoever mastered hydraulic efficiency first would gain enormous industrial advantage. Soon, engineers across Europe and the United States began refining turbine designs aggressively. James B. Francis in America developed the inward flow reaction turbine during the 1840s, creating a system more stable, scalable, and adaptable for varying water conditions. The Francis turbine became one of the most influential machines in industrial history because it balanced power output with operational reliability. It could survive real rivers. That mattered. Early industrial machinery often performed beautifully inside controlled demonstrations, but failed catastrophically under unpredictable environmental conditions. Rivers carried sediment, debris, seasonal surges, ice flows, and pressure variations capable of destroying poorly designed equipment within months. The Francis turbine endured because it was practical. Then came Lester Allen Pelton in the American West during the late 19th century. Mining operations in California required efficient machinery for mountainous environments where water descended at enormous speed, but relatively low volume. Pelton designed an impulse turbine that extracted energy from high-velocity water jets with extraordinary effectiveness. The split-bucket design of the Pelton wheel allowed water to reverse direction smoothly after impact, minimizing energy loss and maximizing rotational transfer. It was elegant engineering born from industrial necessity. Soon afterward, Victor Kaplan introduced adjustable blade turbine systems capable of operating efficiently under low-head river conditions. Kaplan turbines expanded hydroelectric possibilities into flatter regions previously considered unsuitable for large-scale generation. By the beginning of the 20th century, hydraulic engineering had transformed from regional experimentation into geopolitical infrastructure strategy. Industrial powers understood what hydroelectricity represented. Energy independence. A nation with sufficient river systems could industrialize without importing massive quantities of coal or oil. Mountains became strategic assets. River basins became national resources. Hydroelectric development promised not merely electricity, but industrial sovereignty. This was especially important for rapidly modernizing states. Russia, Canada, Norway, Sweden, the United States. All possessed enormous untapped river systems capable of supporting large-scale generation if engineering limitations could be overcome. But hydraulic efficiency changed the equation completely. Earlier generations of water turbines had been useful. Efficient turbines became transformative. A 5% efficiency increase in a major hydroelectric station could translate into enormous additional generating capacity over decades of operation. Nations realized that turbine design influenced not only engineering performance, but economic growth itself. And then electrification accelerated everything. Cities demanded power at scales unimaginable only decades earlier. Electric street lighting spread rapidly across urban centers. Factories converted from line shaft systems to electrically driven machinery. Electric railways replaced horse-drawn transport. Telegraphy, communications infrastructure, refrigeration, and chemical production all multiplied national energy consumption. The 20th century became an age of electrical hunger. Hydroelectricity appeared to offer salvation from the environmental and logistical brutality of coal dependence. Politicians described dams as symbols of progress. Newspapers celebrated hydroelectric projects as triumphs of civilization over nature. The rhetoric became almost religious. Rivers would finally serve humanity. Governments poured enormous funding into dam construction because hydroelectric systems promised multiple benefits simultaneously. Flood control, irrigation, navigation improvement, regional employment, industrial growth, electrification. The turbine sat invisibly at the center of all of it. Without turbine efficiency, massive dams lost much of their economic justification. Reservoirs alone did not create industrial power. Everything depended on converting falling water into rotational energy with minimal loss. This intensified engineering competition globally. Manufacturers like Voith in Germany, General Electric in the United States, and later Soviet and Japanese turbine firms began competing for dominance in hydroelectric technology. Turbine contracts became politically important because large dam projects often symbolized national modernization efforts. The machine itself became propaganda. In the Soviet Union, hydroelectric infrastructure represented ideological victory over nature through centralized industrial planning. Massive projects like the Dnieper hydroelectric station demonstrated Soviet engineering ambition to the world. In the United States, projects under the Tennessee Valley Authority transformed entire regions economically, while simultaneously projecting governmental power during the Great Depression. Hydroelectricity no longer belonged solely to engineers. It belonged to states, and every nation wanted larger systems. Bigger dams created larger reservoirs. Larger reservoirs enabled more stable water flow. Stable flow allowed turbines to operate closer to peak efficiency continuously. Continuous efficiency meant immense electrical output. This logic drove some of the largest infrastructure projects in human history. Hoover Dam, Grand Coulee, Itaipu, Three Gorges. Gigantic concrete walls rose across river systems worldwide during the 20th century because turbine efficiency made such projects economically irresistible. Engineers calculated entire landscapes through the mathematics of hydraulic extraction. The rivers themselves became industrial equations. But behind the optimism stood enormous contradictions. Hydroelectric power was marketed as clean energy, yet constructing large dam systems required staggering environmental destruction. Forests vanished beneath reservoirs. Sediment flows changed permanently. Entire fisheries collapsed after migratory pathways disappeared behind concrete barriers. Communities were displaced on a massive scale. In many projects, local populations received little choice in the matter. Governments flooded ancestral lands in exchange for industrial expansion elsewhere. Villages vanished beneath artificial lakes, while electricity generated from their rivers powered distant factories and cities. The efficiency of the turbine intensified this process. Because highly efficient turbines made larger projects more profitable, governments pursued increasingly ambitious river control schemes. Watersheds became fully engineered systems rather than natural environments. Multiple dams were often constructed along single rivers to maximize extraction potential from every elevation drop possible. The river was no longer allowed to waste energy by simply flowing. Industrial civilization considered unrestricted water movement economically inefficient, and so rivers became segmented, regulated, redirected, and disciplined through infrastructure networks extending across entire nations. By the mid-20th century, hydroelectricity powered aluminum smelting, military manufacturing, rail systems, urban grids, and eventually digital infrastructure itself. Entire modern economies quietly depended on rotational systems hidden inside turbine halls, beneath dams few people ever saw. Most citizens only experienced the final result. Light switches worked, factories operated, cities expanded. But deep inside concrete chambers larger than churches, enormous turbine runners spun continuously beneath crushing water pressure day and night for decades at a time. The machinery became so reliable that much of civilization forgot it existed. That invisibility made the system even more dangerous. Because once industrial society reorganized itself around massive hydroelectric networks, turning back became almost impossible. Entire nations now depended on rivers behaving like permanent industrial assets. And the more efficient the turbines became, the more completely civilization surrendered itself to hydraulic control. Inside a hydroelectric station, the turbine never truly sleeps. Even when the surface appears calm, even when the reservoir resembles an ordinary lake reflecting clouds and mountain light, the machinery below remains under constant pressure. Millions of tons of water wait behind concrete walls designed to restrain forces ancient civilizations would have considered supernatural. The silence above hides violence underneath. At the center of the system sits the turbine runner itself, a rotating steel structure weighing anywhere from several tons to hundreds of tons, depending on the scale of the dam. In large installations, the runner can exceed 20 feet in diameter, forged from hardened stainless steel capable of surviving decades of continuous hydraulic assault. Everything begins with gravity. Water stored high inside the reservoir possesses potential energy created by elevation. The greater the vertical distance between the reservoir surface and the turbine hull below, the greater the pressure generated when water descends. Engineers call this hydraulic head. Industrial civilization learned to weaponize height. Massive intake gates opened slowly along the dam wall, allowing water to enter enormous steel conduits known as penstocks. These tunnels can stretch hundreds of feet through concrete and rock, carrying water downward under immense pressure toward the turbines waiting below. Inside major hydroelectric stations, the sound becomes physical. The water does not flow quietly through the penstocks. It accelerates with a low-frequency roar deep enough to vibrate concrete foundations. Workers inside turbine halls often describe feeling the machinery before hearing it. The pressure pulses through the structure continuously, like the heartbeat of an industrial organism buried underground. In high-head systems such as Pelton turbine installations, water emerges from precision nozzles at astonishing velocity. Some jets exceed speeds approaching 400 feet per second before striking the turbine buckets. The impact transfers momentum into rotational motion with terrifying efficiency. The force is surgical. Each Pelton bucket is carefully shaped to split the incoming water jet in half, reversing its direction smoothly while minimizing turbulence and energy loss. Poor geometry wastes power. Perfect geometry extracts almost everything. That obsession with minimizing wasted motion became one of the defining engineering pursuits of the 20th century. France's turbines operate differently. Instead of relying primarily on impulse force, they function through pressure differentials inside enclosed chambers. Water enters spiraling guide vanes surrounding the turbine runner. These adjustable vanes regulate flow angle and velocity before directing water inward across curved blades. The water changes direction repeatedly as it moves through the runner. Every directional shift extracts energy. Every turbulence reduction improves efficiency. Inside the turbine housing, pressure changes rapidly enough to create one of the most dangerous phenomena in hydraulic engineering: cavitation. Cavitation occurs when local pressure drops so suddenly that tiny vapor bubbles form inside the water itself. When these bubbles collapse against metal surfaces milliseconds later, they produce microscopic shock waves powerful enough to erode steel over time. The damage resembles industrial disease. Entire turbine blades become pitted and scarred from billions of miniature implosions occurring continuously beneath the water surface. Engineers spend enormous effort controlling blade curvature, rotational speed, and pressure distribution to reduce cavitation, because even small efficiency losses become economically catastrophic across decades of operation. Efficiency is not abstract inside a hydroelectric station. It determines heat generation, vibration loads, maintenance frequency, electrical stability, and ultimately, national power output. Kaplan turbines introduced another layer of complexity. Their adjustable blades rotate during operation to maintain high efficiency across changing river conditions. Rivers rarely provide perfectly stable flow rates throughout the year. Seasonal snowmelt, drought cycles, rainfall variation, and reservoir management all alter hydraulic conditions constantly. Fixed-blade turbines lose efficiency when conditions shift. Kaplan systems adapt in real time. The blades twist slowly beneath the water, while guide vanes adjust simultaneously, creating a constantly changing hydraulic geometry designed to extract maximum power under varying flow conditions. Watching the mechanism during maintenance resembles examining the joints of a gigantic underwater animal. The scale becomes overwhelming inside major generating stations. At facilities like Grand Coulee or Itaipu, turbine halls stretch across cavernous chambers lined with generators taller than multi-story buildings. Overhead, cranes capable of lifting hundreds of tons move slowly through the darkness above polished steel rotors, spinning at carefully regulated speeds. The generators themselves transform mechanical rotation into electricity, through electromagnetic induction. Massive shafts connect turbine runners below to generator rotors above. As the turbines spin, enormous magnetic fields rotate inside copper windings, producing electrical current at industrial scale. The rotational stability must remain precise. Electrical grids depend on tightly controlled frequency. Even slight deviations can destabilize transmission systems across entire regions. Turbine governors continuously adjust water flow to maintain exact rotational speed, despite constantly changing electrical demand. The machine is always balancing itself against civilization. When millions of people switch on lights, factories activate equipment, or rail systems accelerate simultaneously, the electrical load shifts instantly. The turbines respond within seconds, increasing or decreasing water flow automatically to stabilize the grid. Most people never realize that rivers are reacting to their actions in real time, and all of it depends on pressure. The deeper the hydraulic head, the greater the stress placed upon every component inside the system. Penstocks endure enormous internal forces, capable of tearing apart weak welds instantly. Turbine shafts must survive continuous torsional stress for decades. Bearings operate under crushing loads while submerged in oil systems designed to prevent catastrophic overheating. Temperature matters constantly. Generators produce enormous heat during operation. Cooling systems circulate water, air, or hydrogen through electrical components to prevent insulation failure. In some facilities, the machinery operates inside environments humid enough to corrode exposed metal, while electrical currents powerful enough to kill instantly flow through nearby systems. The smell inside older turbine halls becomes unforgettable. Hot oil, wet concrete, ozone from electrical discharge, metal warmed by friction, river water moving through darkness. Everything vibrates, even the floor. Workers in hydroelectric plants often develop an instinctive understanding of machine rhythm, because abnormal vibration frequently signals developing failure. A slight tonal change inside the generator hall can indicate imbalance, cavitation damage, bearing wear, or pressure irregularities capable of escalating into catastrophic mechanical failure if ignored. And when failures happen inside hydraulic systems, they happen violently. A ruptured penstock can release water pressure with explosive force equivalent to industrial bombardment. Turbine overspeed events occur when electrical load suddenly disappears while water continues driving the runner uncontrollably. Without proper braking systems, rotational speed can increase to destructive levels within moments. Steel tears apart, generators explode, concrete cracks beneath shock loads. But the most frightening aspect of hydroelectric turbines is often how quietly they operate when functioning correctly. Coal plants announce themselves through smoke and combustion. Hydroelectric systems conceal their violence beneath smooth efficiency. That invisibility helped transform them into symbols of clean modern energy throughout the 20th century. Politicians showcased dams as monuments to progress because the machinery appeared almost elegant compared to the filth of coal infrastructure. No smokestacks, no furnace ash, no endless fuel trains, only water entering a machine and electricity emerging silently from the other side. But that apparent cleanliness concealed the true scale of control required to sustain the system. The turbines only function because entire rivers have already been reorganized around them. Reservoirs flood valleys to stabilize flow rates. Sediment must be managed constantly because accumulated silt reduces storage capacity and damages turbine components. Fish ladders attempt to compensate for migration routes destroyed by dam barriers. Spillways regulate flood conditions through controlled release systems, powerful enough to resemble artificial waterfalls during peak discharge. The turbine is never alone. It exists inside a planetary-scale industrial ecosystem built entirely around hydraulic extraction. And the more efficient the turbines became, the more completely engineers learned to convert natural water systems into permanent mechanical infrastructure. By the late 20th century, some hydroelectric facilities achieved efficiencies exceeding 90% under optimal conditions. Very little energy was wasted anymore. Almost everything the river surrendered could now be harvested. The public rarely sees the inside of a turbine hall during operation. That invisibility is intentional. Hydroelectric systems were designed to appear stable, controlled, almost serene. Tourist photographs focus on reservoirs reflecting mountain ranges or water spilling elegantly across concrete spillways. Governments present dams as monuments to progress and clean energy. School textbooks describe them as engineering triumphs that transformed modern civilization. But deep below the surface, the experience of operating these systems has always been harsher than the image surrounding them. Inside the turbine hall, the machine dominates the body. The noise alone becomes a permanent condition. Even in facilities designed with acoustic dampening, workers spend years surrounded by low-frequency vibration generated by water pressure, rotating shafts, and electrical equipment operating continuously without rest. The sound penetrates through boots and bone before it reaches the ear. Older operators often describe a sensation of carrying the machinery home with them after shifts ended. The vibration never fully leaves. You descend into the station before sunrise. The air changes immediately underground. It becomes cooler near the intake systems, but warmer beside the generators themselves, thick with the smell of lubricating oil and damp concrete. The machinery is already moving before you arrive, because stopping a major hydroelectric station is economically dangerous and mechanically stressful. These systems are built for uninterrupted operation. You enter a world already in motion. In older facilities, maintenance crews worked dangerously close to rotating equipment with minimal protection. A loose tool, unsecured clothing, or single miscalculated movement near exposed shafts could become fatal instantly. Turbine runners large enough to power entire cities rotated beneath thin maintenance platforms, while pressurized systems surrounded workers from every direction. The danger rarely announced itself dramatically. Hydroelectric accidents often occurred through pressure failure, flooding, or mechanical misjudgment rather than explosion. That made them psychologically deceptive. Workers became accustomed to routine because the machinery operated so reliably most of the time. Then something shifted. A gate malfunction, a pressure imbalance, a governor failure, a bearing overheating deep inside the system. And suddenly, the calm industrial environment transformed into a hydraulic disaster zone. One of the greatest dangers inside hydroelectric infrastructure has always been confined water pressure. Human beings instinctively understand fire because flame is visible. Pressurized water is different. It conceals its violence until containment fails. When penstocks rupture, the destruction resembles artillery impact. In 1965, a catastrophic penstock failure at the Baldwin Hills Reservoir disaster in California demonstrated how quickly hydraulic infrastructure could collapse once structural integrity disappeared. Water tore through residential areas with overwhelming force after containment systems failed. Entire neighborhoods vanished beneath sudden flooding. But some of the worst incidents occurred inside the stations themselves. Workers trapped near ruptured pipes or failed valves often had no time to escape. High-pressure water can strip steel from concrete. It can hurl industrial equipment across turbine halls. It can collapse walls, destroy electrical systems, and drown workers inside machinery chambers within minutes. And unlike fire, water fills every available space. Hydroelectric facilities also introduced long-term bodily strain, difficult to measure publicly. Operators spent decades working in environments saturated with vibration and industrial noise. Hearing loss became common. Joint damage emerged from years spent climbing steel structures and navigating maintenance tunnels coated with condensation and oil residue. Then there was isolation. Many major dams were constructed far from population centers because the best hydraulic sites, often existed deep inside mountain valleys or wilderness regions. Entire worker communities developed around remote infrastructure projects, where life revolved around the operational needs of the station. Some workers spent their entire careers inside systems most citizens never thought about. They maintained civilization invisibly, and meanwhile, the rivers themselves were changing. The efficiency of hydraulic turbines accelerated environmental transformation far beyond what early engineers fully understood. Rivers evolved over thousands of years through sediment transport, seasonal flooding, temperature variation, and migratory cycles. Dam systems interrupted all of it. Sediment became trapped behind reservoirs instead of replenishing downstream ecosystems. Fish populations collapsed when migration routes disappeared beneath concrete barriers. Water temperature changed dramatically as deep reservoirs altered natural flow patterns. Some rivers no longer reached the sea consistently. This became one of the great contradictions of hydroelectric power. The turbines produced electricity without smoke, yet the systems supporting them reorganized entire landscapes permanently. And the more efficient the turbines became, the more aggressively governments pursued hydraulic expansion. During the 20th century, entire populations were displaced for dam construction projects worldwide. China's Three Gorges Dam alone forced the relocation of more than 1 million people. Villages vanished beneath reservoirs. Archaeological sites disappeared underwater forever. Forests drowned slowly as rising water consumed valleys transformed into artificial lakes, all to feed the turbine. The machine itself became increasingly invisible as technology improved. Modern turbines operate with extraordinary reliability compared to earlier industrial systems. Computerized monitoring tracks vibration patterns, temperature fluctuations, hydraulic efficiency, and electrical stability continuously. Automated governors respond faster than human operators. Remote systems reduce the number of workers physically required inside generating stations. Efficiency eliminated labor, just as it once demanded it. But replacement technologies are now beginning to challenge even the dominance of hydroelectric infrastructure. Climate instability has exposed one of the system's greatest vulnerabilities. Rivers depend on predictable hydrology. Drought conditions across major hydroelectric regions have reduced generating capacity dramatically in recent decades. Reservoir levels have fallen low enough to expose submerged towns, dead forests, and abandoned infrastructure hidden underwater for generations. Some turbine intakes now operate dangerously close to minimum thresholds during dry seasons. The machine designed to stabilize civilization suddenly faces instability itself. Solar and wind systems continue expanding because they distribute generation across broader networks rather than concentrating it within massive centralized dams. Smaller renewable systems reduce the catastrophic risk associated with large hydraulic infrastructure failures. But hydroelectric turbines still remain among the most efficient large-scale energy conversion systems ever created. That fact continues to shape modern civilization. Even now, enormous turbine runners continue spinning beneath mountains, rivers, and concrete walls across the planet. Hidden inside cavernous halls, they convert gravity into electricity, with efficiencies engineers from the 19th century could scarcely imagine. And yet, the deeper legacy of these machines extends beyond power generation. The turbine changed humanity's relationship with nature itself. Before hydroelectric infrastructure, rivers were forces civilization adapted around. After the turbine, rivers became industrial assets expected to perform continuously according to economic demand. Water stopped being merely part of the environment. It became infrastructure. That transformation may be the most important consequence of all. Because once industrial civilization learned how efficiently nature could be converted into energy, it became almost impossible to stop searching for new systems to optimize, redirect, and consume. The turbine taught humanity that even a river could be disciplined into serving the grid. And once that lesson was learned, the entire planet slowly began entering the machine.